And so it's pretty straightforward topic. It's somewhat rule based, but it doesn't really have to be, because just like in the first unit, when we discovered the relationships between rectangular coordinates and polar coordinates, we can discover the relationship between cylindrical coordinates and rectangular coordinates. So we'll do that somewhat, but we're not going to go too crazy with it. So the idea here is that you're looking at a unit circle with height. Right? That's what the cylindrical coordinate system really is. Right? You have some angular measure. Right? That angular measure corresponds to an x and y value. Right? That x and y value is r cosine theta, r sine theta, just like it was in the first unit. The only difference is we now have a z to worry about. Right? But z is still z. Right? It's still the height off of the xy plane. Right? Whether it's positive or negative depends on the situation. So instead of having, like in the first unit, xy becoming r theta, now it's going to be xyz becoming r theta z. Right? So as long as you know how to convert over into polar coordinates, this is really no challenge whatsoever, because these formulas are all the same as they were in the first unit. That's why we spend so much time on that stuff. Right? So, oh, that was weird. You know, no matter how many edits I make, I still can't fix everything, I guess. Bless you. Plot the point. I plotted it for you. Yeah, so typo bonus for somebody. Convert the cylindrical coordinates into rectangular coordinates. That's what it should be. Jeez Louise. It's always something. Anyway, we have an r, a theta, and a z. We're not worried about the z. We're just worried about the r and theta. All right, so x is equal to r times the cosine of theta. Y is equal to r times the sine of theta. So 4 cosine 2 pi over 3. 4 sine of 2 pi over 3. And what is the cosine of 2 pi over 3? Yeah. Negative 1/2, yep. And what about the sine of 2 pi over 3? Square root of 3 divided by 2. Good. So negative 2 and 2 rad 3 are our x and y values. So in rectangular coordinates, we'd be looking at negative 2, 2 rad 3, geez. And negative 2 is the z value. That remains unchanged. And so we're not worried about converting that. Now when we get to spherical coordinates, next class, maybe 2 classes from now, that'll change. But for now, that's not too bad, because it's relying on prior knowledge. Right? Prior knowledge sometimes is a good thing, except apparently when it comes to the unit circle. So going the other way, converting to cylindrical coordinates. Well, we're starting off with an x value and a y value and a z value. And we need r theta z. Right? So the z is, again, not something we're concerned with. It's just the x and y. Right? So I'm going to use a formula that'll help me figure out the value of r. R is equal to the square root of x squared plus y squared. All right, so the square root of 1 squared plus 3 squared, negative 3 squared, which is 9. So it's going to give us root 10. All right, so I have the r value. Now I need the theta value. All right, so if I were to just draw a quick sketch of this, the x value of 1, the y value of -3, we have the hypotenuse of 10, we just figured that out. You don't necessarily need a diagram, but for me personally, I like the diagrams because it lets me off the hook when it comes to memorizing formulas. So I don't need to necessarily remember that theta is equal to the arctangent of y over x, right? Or theta is equal to the arcsine of y over r, or theta is equal to the arc cosine of x over r. I don't need to know that if I have this, because I can just create those rules as I go. All right? So when I look at this, I might say, okay, the tangent of theta is equal to -3 over 1. So just -3. And then solve for theta. Theta is equal to the arctan of -3. Now, sometimes it's okay to leave it in that form, but that's pretty rare, so we'll actually just figure it out real quick. My mode, radian mode, arctan -3. Talking -1.249 roughly. And that's radians. Yeah. -3 is not a clean ratio. It's not a ratio that you would find in the unit circle. So I'm not worried about trying to find this in terms of pi. If that were a radical 3, that would be a different story, but that's not the case. All right, so my final answer here is always going to be in the form, when we're going to cylindrical coordinates, r, theta, z, we're looking at rad 10, -1.249, and the z value is 5. All right. Now, you might look at this and say, okay, cool, we're learning a new way of representing coordinates in 3 space. That's wonderful. What could this possibly be useful for? Okay? So we get to number 3, where we start talking about actual equations. Now, these equations vary in difficulty, but the idea is that sometimes an equation is more conveniently written in polar form than it is in rectangular form. Right? So cylindrical form, again, is how we represent polar equations in 3 space. Right? So by converting this over into rectangular form, we can get a look at what this equation might be, or what it might resemble, what it might be in terms of a standard form. R squared is equal to x squared plus y squared. So this is the same as saying x squared plus y squared plus z squared is equal to 9. That's the equation of a sphere. All right, so that's the equation of a sphere. Now, I don't know if this necessarily proves my point, this particular problem, because if I was looking for something like a volume, by identifying it as a sphere, I might not even use calculus to figure out the volume. I might just use 4/3 pi times radius cubed. But if I needed to use calculus, if I needed to use multiple integrals, in this form, I have 3 variables. In this form, I only have 2 variables. Dial down the number of variables, you're dialing down the level of difficulty. Right? So it's a matter of convenience. In the case of the second one, it doesn't really look like it's really anything that can be changed overly, but if we know that theta, again, we could draw a diagram if we want, but the idea was that the theta could be represented as the arctangent of the y value divided by the x value. Right? So I can make that adjustment. So arctan y over x would be equal to pi over 4. The idea being that I can take the tangent of both sides and make this y over x, I think I said y over 4 before, would be equal to 1 which leads us to the equation y equals x. All right, so just by taking the tangent of both sides, because if I take the tangent of the arctan, that cancels out. Tangent of pi over 4, unit circle, tangent of pi over 4 is equal to 1. All right, so we get y over x is equal to 1, which gives us this equation y equals x, but it's in 3 space, so this is not the equation of a line, it's the equation of a plane. All right. Now, both are relatively simple equations, y equals x, theta equals pi over 4, but the tie goes to the one that involves a constant. All right? Pi over 4 is going to be easier to integrate or differentiate than x. Not overly, but it's still nicer. All right? The last one, z equals r. I could say z is equal to the square root of x squared plus y squared. Now, that one in and of itself might not seem like something that would be instantly recognizable, so maybe you square both sides. And then get it into standard form. X squared plus y squared minus z squared is equal to 0. All right, now you don't know this yet, but starting, I guess, as early as this evening, you'll start to get to know it. This is the equation of a hyperboloid.
What is a hyperbola like?
I will show you. Talk about the calculus of it, because when we talk about multiple integrals, we're trying to get an area under a surface, you know. So it may be a rectangular area, you know. So the portion on the xy plane may be rectangular in nature, maybe it's not, but we are generally looking for the volume contained between the surface and the axis itself, right? So this will do that for us, but in a different way, right? So a couple of diagrams here for you. This is what the areas would look like in rectangular form, but this is a top view, right? So you have just some arbitrary region on the xy plane, and then you have a surface that's floating out here in space. These rectangular prisms are coming out of the page, and each one would have a volume, and if you can get infinitely many of them within that region, then you'll have the actual volume contained between the surface and the xy plane. All right? The same idea holds for polar coordinates, except we have to use polar notation. All right? So instead of coming up with the area using base times height like we would for a rectangle, or volume, length times width times height, we have to do it using circular measures. All right, so S equals r theta for arc length, 1/2 r squared d theta to come up with an area in a bounded region, things like that. So that leads us to the formulas that we're going to actually work with. I do want to take a few minutes, because here's one derivation of the formulas that we'll work with, but I like a different one a little bit better. And so I'll take you through that right now. / you'll be on the hook for it. So if you needed to find the volume of any kind of figure, it would be length times width times height in rectangular form, right? But let's just focus on the area for a sec. All right, so area we would say on an interval, we would say change in x times change in y, but we want it on an infinitesimal level, so I'm going to say dx dy. All right, because we know that all we have to do is multiply it by the height, and that area becomes the volume. So this really becomes the most important aspect of a multiple integral, all right, or iterated integral. Right? So if I can convert this over to polar form, then I'm going to be in good shape. All right? In order to do that, I need a couple of pieces of information, really important pieces of information, like x is equal to r cosine theta, and y is equal to r sine of theta. And we're going to differentiate those. All right, so I'm going to take the derivative with respect to theta, dx d theta. Really doesn't matter if you do it with respect to theta or r, it all comes out in the wash. I'm just choosing to do it with respect to theta. All right, so first function r times the derivative of the second, which would become negative sine theta, plus the second function cosine theta times the derivative of the first, which would be dr d theta. Ultimately, I'm just looking for a dx, so I'm going to run through with a d theta and make it dx equals negative r sine theta d theta plus cosine theta dr. All right, these are rules that we worked with back in the first unit also, but that was like February, so not fresh. Let's just put it that way. So dy d theta, r times cosine theta, first times derivative of the second plus the second sine theta, times the derivative of the first, which would be dr d theta. And again, clean it up. And multiply everything by d theta. And we get dy is equal to r cosine theta d theta plus sine theta dr. All right, so now what I need is the product of dx and dy. All right, so dx dy is going to be these two bad boys multiplied together. So a little distributive property. A lot of distributive property. So negative r squared I always do it this way, but I just want to see, I'm just thinking it through real quick, if it's easier to do it a different way real quick. Because eventually we're going to have to take the limit of this as theta approaches 0. If I do that, yeah, that's going to be better. So the limit of dx dy as theta approaches 0, right? And that's because, yeah, we want to have infinitesimal x and y, but we also want to have infinitesimal changes in theta and also infinitesimal changes in radius, right? So by limiting this as theta approaches 0, it's going to simplify down, number one, but also it's going to allow the parameters to close in on the most infinitesimal value.
So it's not the change in theta, it's the actual value in theta that's approaching 0?
Oh, sorry. Let me make sure I'm thinking of this correctly. Yes, it is the theta.
Okay.
Yeah. Because the d theta is already infinitesimal. We want the theta to also become infinitesimal. Yeah. Okay, so on the right-hand side, so I'm going to find the limit of this whole shebang here as theta approaches 0. Anything that has a sine in it is going to go away. Anything that has a cosine in it is going to go to 1. So I'm going to get, from the first binomial, the whole thing collapses down to just a dr. And in the second binomial, it collapses down to just an r d theta. Bless you. All right, so from this we get r times dr d theta.
Isn't Simon 0, 0?
Yeah.
So what value is not r?
So this is zeroing out.
Oh, I'm sorry. I was looking at the middle part as it was the first part. Never mind.
Oh, got it.
I see what.
All right, so that's actually the, I think the better origin story, the more calculus-y one. This is all geometric. It's differences between areas, and that's good too, I guess. But I like this one better. Actually, I really like it better now because if you look at my answer key online, you'll see that I brute forced it. I distributed this all out before. I was like, oh, now I'll apply the limit. And then it was only in this moment where I was like, oh, I could also not distribute it out, but still apply the limit, and it's still going to work. So, brains.
That's
Mm.
So let's say you did distribute it out, you would have at some point get like a dr times a dr. What happens?
dr squared.
Okay.
Eventually it cancels out with the limit, but you'd still have a dr quantity squared. All right, so that leads us to these rules, which they look messy, but they're the best form of the rule, the Fubini's theorem. It's the same general idea as it was for rectangular coordinates, where instead of dx dy, it's going to be r dr d theta, right? The f of r theta, that's your z, right? So, but the z equation converted to be in cylindrical form, not in rectangular form.
Yeah, so I just want to know what happened when we went from dy to dx dy. Like, from that line to the next line.
Give me colors.
From the red line to the black.
Red line to the black. Oh, okay. So what I did was I took these two things, because I'm multiplying dx and dy. I'm multiplying that by that. All right. So when we're evaluating a function, I mean, this looks nasty. I mean, in terms of finding an antiderivative,
Is that why you color code all your work?
I try. It's not always as consistent as I would like it to be, but instead of being like the 14th step down, like purple, man, it's the purple one. So yeah, so we have to convert this over into polar form. Well, we don't have to. I mean, the directions tell us to, but if we were just given this iterated integral, you might say, I'm not gonna convert it over. I'll work with it as is. And my answer to that would be best of luck to you. So, I mean, you'd be kind of in a jam because of that inner function. It's pretty crispy. Anytime I see x squared plus y squared in an integrand, I'm automatically thinking polar form, right? Because x squared plus y squared is equal to r squared, and you already have a substitution that you can make. It's just a question of everything else, right? Because everything has to be converted over, not just what you want to convert over. You know, it's kind of like U substitution for integration of a definite integral. The number of times I've seen people perform the U substitution correctly, but then never change their bounds, and then get the answer wrong because of that. It's uncountable. I can't even put a number on it. Right, so you have to change everything over, and having an organized approach to it is the name of the game here. Let me try that again. So I'm going to focus on the inner one. innermost one for a second. All right. So that definite integral is with respect to y. So what that tells me is that these two bounds are really y equals. Now, it's probably something you would have assumed because the expression itself is in terms of x. So what else would it be equal to? Yeah, that's fine. But it really wasn't for the purpose of understanding these bounds that I'm emphasizing this. It's these two guys. Because these two are with respect to x, so that makes this an x equation. X equals 2 and x equals 0. All right. So I'm going to look at my bounds first. All right, because the bounds are always going to be locations that you can find on the xy plane. All right. So I'm looking at y equals the square root of 4 minus x squared, and also the negative version of that. All right, so I'll just do that all in one shot, plus or minus. All right, because whenever I see a radical function containing an x squared, I'm thinking conic section, specifically in this case circle, but you don't really know unless you have a lot of experience with this until you start messing with it. All right, so I'm going to square both sides and get everything over, well, all the variables onto the same side. So I get x squared plus y squared equals 4. All right, so that is a circle with the center at 0, 0, and radius equal to 2. All right. Now, we can also get that in polar form, but fun fact, good thing about the circle equation, once you've identified the radius, you put it in polar form. All right, because x squared plus y squared is equal to r squared. R squared is 4, therefore r is equal to 2. So we got it without really trying to get it.
Would it be plus or minus 4?
Plus or minus 2?
Or 2, I guess that 2 as well, yeah. Because like when we squared away the square root, plus or minus 1 away as well.
Yeah, because when you square a negative or a positive, it goes to positive either way. Yeah. So, quick sketch of this. Drawing the tick marks, and then I'll completely miss all of them. Mostly. All right. So I'm still kind of living in rectangular form, but we eventually have to convert it over to polar. But I want to get an idea of what the base region is looking like. All right. So in terms of y, it's telling me that I'm living between negative the square root of 4 minus x squared, which is the bottom part of the circle. So this guy over here is the negative square root of 4 minus x squared. And then the top part, I'll just bold that. That's y equals the positive square root of 4 minus x squared. All right. So it's telling me that I'm accounting for all y values between this bound and this bound. So from bottom to top. All right, that's easy enough. But then in addition to that, I also have to live in between x equals 0, so between x equals 0 and x equals 2. All right, so that's telling me that I'm starting here and populating out in the positive direction, stopping at 2, all right, because that's right here is 2. All right, so this is the base region under the function. All right, so it's not an entirely circular region, it's a semicircular region. But at least now I have an idea, right? Because I now need to convert this over into polar form, but I also have to convert over the bounds into a reasonable set that are related to the base region. And you know, with polar, you know, there's a lot of wiggle room because we can define in a lot of cases anyway, we can define the same region using different approaches. But in this case, it's semicircular, so it should be pretty straightforward. All right, so I need to redefine my double integral. I'm still going to have a function, but it's y squared that's going to get replaced with an r sine theta squared. Clean that up. And then x squared plus y squared is the same as r squared. And then I'm going to tack on an r, so times r dr d theta.
Wait, why, I'm sorry, why did you do the R, D theta?
Because of this. Because that's what dx dy is equivalent to. All right, so now we have that. It's a mess, but it's in polar form. Our bounds aren't. We still got to take care of that. But we can clean this up a little bit. R squared sine squared. This would be r cubed, this part, but then I have another r, so r to the fourth dr d theta. You can combine the steps if you want and get r to the sixth sine squared theta dr d theta. Still haven't addressed the bounds. All right, the first bound should be in terms of r. All right, so I need r values only. Okay, I'm going to redraw the picture, probably poorly again. I'll do it right underneath. All right, so when we're talking about r, we're talking about radii. Radii related to circles. All right, so we're not talking about lines anymore, rectangles, things like that. We're talking about arcs. All right, so what I would want to do is start off, or at least consider what the smallest r value would be. 0. That would be the one with no radius. All right, then an infinitesimally larger r value, then even larger, 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 and so on, until we get all the way out to what? 2. So 0 to 2. All right, definitely a lot nicer than writing the square root of 4 minus x squared, positive or negative. All right, now in terms of the theta values, I gotta say it again.
I'm sorry, negative pi over 2.
Negative pi over 2 to positive pi over 2. All right, all we're doing is looking for what part of the unit circle contains the base region that we're interested in. All right, now we're at a point where the integration process is not difficult. I mean, we looked at the original one, that was nasty. This one is nothing.
Why is it going backwards? Negative pi over 2 to pi over 2? Why not?
Oh, because of the size relationship. So we could call that 3 pi over 2, but if you went pi over 2 to 3 pi over 2, it would give you this.
Oh.
So we want to capture that particular region.
Wait, I'm sorry, I can't. Can you go over where we got 0, 2 from again? For points of 0, 2?
So since we have to populate this space here with infinitely many semicircles, we start off with a circle with a radius equal to 0. So that's a 0. And the most we could ever get in here is a circle with a radius of 2 and everything in between.
And we figured that out from before, right?
Yeah, from this diagram.
Yeah. And that's,
Why didn't
and we
do
got that 2
pi
from
over
before
2
because the original
instead of
2.
Negative pi over 2? At the bottom. Sure.
Because 3 pi over 2 is bigger than pi
Yeah,
over 2.
which would have given you the negative version of going around the other side of the circle, which is a good one.
No, 0 from 0 to 2.
No, it's on the bottom, you would have,
You're going all the way around, we only need this first half.
no, 3 pi over 2 to pi over 2, so that's the bigger on the bottom, so if you want to write it with the smaller on the bottom, that would be the negative equivalent of going from pi over 2 around that side, which
Right.
is equivalent to just doing the side of the circle that we're talking about.
Right.
Okay.
Yeah. And 1,000 over 500 is equal to 2, but I'm not writing 1,000 over 500. I'm going to go with the path of least resistance here. Yeah. So, yeah, either way, whatever works. And that's what I was talking about before. The idea that polars are nice because you can represent the same idea using multiple ways and still be correct. Okay, so this the inner integral, we're anti-differentiating with respect to r. So we're leaving the theta stuff alone. So if I just focus on that guy, I like to just pull it out and work on it separately. So this would be 1/7 r to the 7th sine squared theta over the interval of 0 to 2. All right, so 128.
I didn't know the center was at 0, 0.
Based on the circle equation. X squared plus y squared means that the center is at 0, 0. So there's no h and k value.
If the center was not at 0, 0, you can still say that your radius, the balance for integration of the radius is still starting at 0, right? When it's a circle, you can still say that your balance starts at 0.
Not necessarily.
It doesn't matter, right, though, because it's a circle. So no matter what, you can always change your origin wherever you want.
Yeah, I mean, you could translate your function, yeah, but it would impact what the base region is, and if that's the case, like for example, if this is translated, let's say 1 unit to the right, then you're going to have more area covered between 0 and 2, and so that would be it would be a different figure. And in
So
fact,
you
you'd be able to go from 0 to 3.
You would actually have to change your function then?
You'd have to change your bounds. Your upper function is fine because that's hovering over the base region, but your bounds might be impacted.
Oh, so if you moved it over 1, you would just say from 0 to 3.
0 to 3, but then that could impact what your theta values are because it might not be where you think it is. All right, so assuming that's correct, then we get to a point where we can integrate this with respect to theta, again on the interval of negative pi over 2 to pi over 2. And that, you just pop that right in a calculator, right? Because we can do the antiderivative of sine squared, but it involves a trigonometric substitution. You're welcome to do it. You're also welcome not to do it. And give me less to have to worry about grading.
Do you mind giving an example of where like the center of the circle would be at some random spot, and then how that would affect our theta?
We're getting there. All part of the act. So sine.
Pi over 7.
That sounds familiar. Yep. So in decimal form, 28.723 approximately. You end up with the exact value of 64 pi over 7.
Are we ever going to go over that problem from the prior revision of this packet where we were getting different answers?
Which problem is that? Ron. compute the volume of the solid formed by the intersection of the surfaces. Right? So the tech assignment is really going to kind of drive home the idea of what these quadric surfaces look like. Right? So you don't have to instantly recognize what's what right off the bat. Once you start working through the tech assignment, it'll start becoming more second nature. That being said, size relationships are still a thing. So here we're taking, again, I edit, and then this is what happens. Should be z equals. There's a z missing.
It's on our page.
No,
On our paper it says E.
Yeah.
It's just yours.
Okay. Well, that sucks. So anyway, you have 5 minus x squared minus y squared. So you're looking at a negative relationship here as opposed to a positive relationship. So one of them is going to be opening upwards, the other one's going to be opening downwards. If you had to take a guess which one's going to be opening downwards, it's probably the one that involves a negative. All right, so there's the educated guessing component. But there's better ways, and that's what we're going to get into. All right, so we know that the bounds are always going to be important. So there's never a bad time to start considering those. But since, and it doesn't say directly that we should do this in cylindrical coordinates, but I mean, we should, because we just learned about it. And also, there's the key indicator that I mentioned is that if I see an x squared plus y squared, that's tailor-made for cylindrical coordinates. All right? So because x squared plus y squared is equal to r squared. So I know right off the bat that I have a substitution that's ready to rock and roll. Z is equal to r squared. Z is also equal to 5. I mean, I'll just manipulate this really quickly. 5 minus, right.
I'm sorry. Yeah, 5 minus y.
If you factor out the negative, you get x squared plus y squared, which is also r squared. All right, so we have those two relationships that we can build off of, and that's going to get us into polar form. All right, since they're both equal to z, they're both equal to each other, we could say r squared is equal to 5 minus r squared. Add r squared to both sides and solve. Divide and take the root, and you get the square root of 5 over 2. With polar coordinates, we don't account for the negative because the negative is just talking about a direction. Okay?
5 plus r squared now?
Would it be, say it again?
Would it be 5 plus r squared?
Less. So when we pull out the negative sign here, that's going to translate. This part itself becomes r squared. So you're talking about this?
Basically, so you had the x squared minus y squared. Wouldn't that equal to negative times
The x squared minus y squared itself isn't anything. The negative x squared minus y squared, that's the opposite of r squared.
Okay.
Oh, okay.
All right, so dividing by 2, taking the square root, we get root 5 over 2. We don't need the negative because, again, it's a radius. If you're talking about a circle's radius, like if you go, the circle is in every direction already. If you take radical 5 over 2 steps in the negative direction, it doesn't amount to anything, right? Anything unique anyway. So this is a circle with center at 0, 0. And the radius is stated, right? So I can draw that poorly. And that's going to help me get a sense of the bounds, all right? Because I know that eventually I have to develop an iterated integral that's going to convert this over into polar form. So r's and betas are the name of the game, all right? So if I'm going to be bounded with this base area, then that's really good news because I'm looking at an entire circular region which means that if I want to cover this region with circles, I would start with a circle with radius 0 and then increase outward until I got to a radius of root 5 over 2. Oh man, this is spiraling out of control. All right. I'm also covering the entire circle, which means that I'm starting at 0 and I'm swinging all the way around to 2 pi. All right? It's not like that other problem where we only wanted half the circle. This time I want the whole shebang. All right? We're not given any restrictions in the problem, and there aren't any natural restrictions based off of the solution to this. So we're in good shape. I have my bounds. Now it's just a matter of having the function itself that I'm looking to integrate. Right? So what I want is, just like in Calc 2, when you're looking for the area between two curves, you want the dominant and then the non-dominant functions, and you subtract them. Same idea here. I want to take the one that's facing downward and subtract from it the one that's facing upward. Right? So in order to do that, I'm going to set up my iterated integral. I have my z equations in my polar form, which is what I want. Z is r squared, and z is also 5 minus r squared. Right? The one that's facing downward is the 5 minus r squared. Right? And it makes it look very much like a parabola when you do it this way. Right? If you put it in polar form, it becomes a little bit more obvious which one is the upward facing and which one's the downward facing. Because again, we're taking, when we go cylindrical polar form, we're taking it from 3 variables down to 2 variables. Right? In most cases, the z stays put. Right? So the x, y values converge into an r. Right? So we're looking at really 2 parabolic equations. This one faces upward, based on algebra 1, and this one faces downward, also algebra 1, college algebra, whatever. So I want the downward facing one first, and I'm going to subtract from that the upward facing one. And I'm going to multiply all that by r dr d theta. I mean, you can probably guess what the most commonly forgotten step is when it comes to stuff like this, assuming people know what the hell they're doing. Dy dx doesn't just become dr d theta. It's r dr d theta. That little r makes a big difference. All right. So we'll put the bounds in a second, but I'm going to clean this up. This part here is 5 minus 2r squared. So run it through with an r. 5r minus 2r cubed dr d theta. All right, so I know what my bounds are for r. I'm starting with a circle that has no radius, and I'm maxing out at a circle that has a radius of radical 5 over 2. In terms of the angle, I'm going around the entire circle. So I'm starting at 0, and I'm going to 2 pi. Antiderivative is not crazy, because we're looking at something that is exclusively in terms of r. It's all power rule. So 5 halves r squared minus 1/2 r to the 4th. On the interval of 0 to root 5 over 2. So that one step you have to do out in order to take advantage of your calculator in the next step. All right, so we're looking at 5 halves root 5 over 2 squared minus 1/2 root 5 over 2 to the 4th. Not going to bother subbing in the 0 because that's going to cancel out anyway. All right. So root 5 halves squared is just 5 halves, so 25 fourths. Minus root 5 halves squared would be 5 halves squared. Again, you get 25 fourths multiplied by 1/2, 25 eighths. So that's going to give us 25 eighths. Not our final answer because I have to integrate that with respect to theta over the interval of 0 to 2 pi. Not something that we need a calculator for, as it turns out. It's just 25 theta over 8, going from 0 to 2 pi. Pop in the 2 pi. And you get 25 pi over 4. And so that would be the volume contained within those two surfaces. But it comes down to this. I mean, this is the key to everything. You don't get those bounds without knowing this. All right. So, and the reason I would know to be able that my first step should be to try to set these two equal to one another. That just comes from the idea of, well, what's going on here. You know, you have two surfaces that are intersecting each other, right? So the outer limit of the actual volume has to be wherever that intersection is, right? So it makes sense to figure that out, right? And the part that would contain the least volume would be at 0, where you haven't moved at all, right? But finding the intersection is usually step 1 when it comes to finding the bounds, right?